All right. So it's compilers week 6. And we do have a test today. But I'm going to talk for probably for a few minutes, or 45 minutes or so before we take the test. I think the first thing I want to do is actually talk about homework 3. So let me grab that. It's particularly the left recursive, right? But so I probably want to go over that before I do anything else. But what's due? Excuse me. This is I think these are the wrong slides. That's it. Okay. Sorry, I grabbed the wrong slide. Okay, this is the slides. I knew I had a lot more information on this. Okay, so if you haven't gotten your pen, if you're my advisee, I have yours. So come see me during the break or after you're done with the test. There is a career fair next Wednesday from 4 to 7 here in the building. And I will send out something this week, so watch for my email for extra credit opportunities. And I won't actually be on campus on Saturday. There's a meeting I have to go to in Sandy somewhere that way. Which way? That way. Okay, so I would just be driving back from Sandy. But I'm available for Google Chat if you need to chat with me on Saturday during lab time or anytime over the weekend if you need to talk to me. That I actually moved the labs to next Monday instead of Saturday, partly because I won't be here Saturday, but also someone told me that you like to have the whole weekend. If you work during the week, and weekend is the only time you can actually work on labs. So I'm giving you Saturday and Sunday. So it's actually due Monday night. And part B is going to be due the Monday after that, the 22nd. And part A is really just getting your grammar in the recursive descent parser and make sure it parses your sample program. So yes and no. All right. So your main is just going to call this function program or whatever star symbol, and it's going to come back with either true or false, and you report that. That's it for part A. And part B is when we go in and actually add a little bit more error messages. We bring back our symbol table. If you declare a variable, you want to put that variable and the type into the symbol table so you can tell whether a variable has been declared before you use it. We're not doing type checking yet, but you should be able to say, have I seen X? I'm using X here, but was X even declared? So a symbol table will tell you that. I have the project almost, I'm changing some stuff from last year, so I'm going to post that. I'll make that available sometime this week so you can take a look at the project and you can work in pairs for the project. As far as announcements, let's see. We're going to start the topic, our next parser, which is the LL1 parser, by computing the first and the follow sets. Okay, those are, again, it's grammar manipulation or modification. It's not modification, but it's really taking the grammar and pull stuff out of the grammar and that we could use. And that stuff that we pulled out is actually going to go into a table form. And then we're going to parse just by looking at the table. Okay, so instead of before, remember where the recursive descent is by function. So I'm in this function. I have a token. I got to go pick a rule that matches that token. Right? So is there either going to be if the token is this, well, if a token is that, else and else and else. We got a bunch of if and else's. A table-driven parser is a table lookup. I'm in this rule. I have this token. What should the rule be? It's strictly one token look ahead. Fong and his group just left. I'm not sure where they're going. They've been going from one office to another office. So strictly one token look ahead. You cannot have two entries in that table. This token, this rule, it's got to be that. Okay, so and by computing the first and follow sets and constructing this table, we could actually uncover these problems. It's like, wait, I got this cell is too crowded in the table. Like it's got too many things. They only have one rule per cell. And I don't even have to think about it. LL1 parser is fast. It's like boom, boom, boom. Table lookup, table lookup. And we're going to look at how we're going to represent the table. The table is going to be very, very sparse. So some rules, you just have like one token, right? And nothing else. But you got to take care of all of the tokens. So we're going to take a look at that. But before we get any further, this is last week's in-class exercise. I had a slide with the problem. I posted as an in-class exercise, but we put the answers on the board, but I never actually put answers on the slide. So I thought I'd put it on here so you can see kind of what we did. And in general, if we take look at one of the homework questions, pen. Okay, take a look at one of the homework questions. If you have a rule, you have S that has 4 separate rules. Some are non-left recursive. One is right recursive, which is fine, completely fine. The only one that's left recursive is this one. Okay. Yes, I also asked you to remove unit productions, and some of you did that first. That's fine. By removing unit production just means you're going to have more productions for A and more productions for B. Okay, none of those have a left recursive S in it, which is okay. I don't care if they're big symbols on the left-hand side as long as it's not S. It's the S going to S. That's the problem. Right? That's the one we're addressing. Okay, so if we're following the algorithm, we're going to take this out. Okay, we're going to take this out. Okay, but we're going to move it. We'll still need the recursive S, the C. Right? This is the recursive part. I still need that C, because otherwise I'm not going to get any more C's. So I still need a C. Okay, but instead of a left recursive, I'm going to make a right recursive. This will still give me C's. Okay, I'm just going to call it X instead of S, otherwise, because I don't want to change whatever S is. Okay, so yeah, this will still give me C's, but I also need to put a lambda in so we can say, no more. I don't need any more C's. Right? I didn't have to do that up here because it was a left recursive. If I didn't need any more, then I'll just pick one of these rules and I wouldn't have any more. That one has a right recursive, which you also have to take care of it. But if I didn't want any more SCs, I'll just stop it with one of these 3. Okay, so that's the bottom of the tree before. Right, so, but this C's here, let's take care of that little C. Okay. Then you just go back to the original productions. The A, the B, and the DS. You have to change those, but you have to add the little C's onto them. Okay, so that will make sure you start with A, little C's after. You start with B, big B, bunch of little C's after. You start with DS with a bunch of little C's after, which is exactly what I said there. Right, left recursion. Keep giving me C's, keep giving me C's till I don't want any more C's and cap it off with A, B, or DS. But the way on the bottom, that's actually the start. Everything else comes back up, trailing C's. Okay, that's what this means. So now I have a right recursive grammar. I start with the A, and gives me C's after. Start with a B, gives me C's after. Start with a DS, gives me C's after. Okay. I don't need a C in S because C is taken care of with X. Okay. There was one that was slightly trickier. This one. Right over here. B goes to big B, AA, or big A, B, or lambda. Okay. If you didn't have this, if you didn't have the middle one, you just had the big B, AA, and lambda, things are easy. Just switch it. The lambda doesn't affect anything. Whether lambda is the very first lambda or the very last lambda, is still a lambda. Right? So if you didn't have that middle one, just switch it. But because you have that middle one, okay, it changes the grammar if you simply switch the B's. So we're going to do the same trick as we did over here. We're going to take this out first, okay, by moving it. I still need the AA, so I'm just going to move it to the end and make sure I have a lambda so I don't need any more. I can, no more. Okay, so that took care of the AA. I'm still getting a bunch of AAs. Then B is, okay, B is ABY and lambda Y. Okay, if you just leave it at lambda, it's not quite right. Okay, because this one I could still get. It turns out Y is also a unit production at this point. Okay, so some of you said, oh no, you asked us to remove all unit productions as well. Yes. The correct answer for this will be correct answer will be, yeah, you could remove the lambda, remove the unit productions by moving what Y is down. So review on the unit productions. Here is a Y by itself, a unit production. What is Y? That thing. Well, move it down. Make it that thing. That's the Y. Right? I'm gonna have to change it. Don't change the B's to the Y's or the Y's to the B's and start making other changes. Just take the unit out and put in whatever that Y is in. That's how you yank out the unit productions and substitute it. Okay, so let's review both. Left recursion, also unit production removal. Okay, so here, if you take a look at this, okay, E goes to E plus, E goes to E minus, both left recursion, move it to the end, call it X, plus TX minus TX, lambda, right? And this one, non-recursive, add the X, TX. Okay? Same thing here. T goes to T, recursive. T goes to T, recursive. Move it to the end, call it Y, okay? And a lambda. And then T goes to F, Y, right? And then this one, which is, yeah, this one's not recursive, not involved at all. Okay? So that's how we do the left recursion removal. Any other questions about that? I think most people had trouble with that. Left factoring, I think most of you got just fine. So this particular grammar, before we removed the left recursion, we had opportunities for left factoring. These two rules are the same. Those two rules are the same. Okay? But after we move it out of the way, Okay, after we move it out of the way, we don't actually need left factoring anymore because the plus minus, those are different rules, times divide, those are different rules, right? Actually makes it a little easier. Right. Okay, so if you had questions, I think homework 3, I printed everybody's out, but you should have gotten scored anyway if you turn it in. So check your Blackboard, make sure the scores, I recorded the scores correctly. If I checked off your lab 1 already, you have a score. If you turn it in, but I haven't seen it yet, it's still in there. Okay, so if you're ready, see me after class today or sometime this week. I'll be here tomorrow, Wednesday, and Thursday afternoons. So if you need to talk to me in person, I'm here all week. Okay. Right, so recursive descent is your lab 2. Look at that sample code. It doesn't do the tokens stuff for you, but it sets up some functions so you can see how the functions flow. But today we're going to start looking at, it's because of time, start looking at the LL1 parser, which is also a top-down parser. Like I said, this is a table-driven. The name is always really interesting. Actually, the 2 L's, the second L is the more interesting L. The first L was sort of given. I don't know why it's there. So the first L says the input is read in from left to right. Okay, this is not like some Asian language or something. Okay, but interestingly enough, I know at least one programming language where the input is read in from right to left. So you evaluate kind of backwards. Okay, the APL, which is an experimental research language, is actually read in from right to left, and that's how it gets evaluated. It probably shouldn't matter because what matters is where am I getting the next token? Is the next token here or is the next token here at the end? Well, it doesn't really matter. So the first L is not really that remarkable or interesting, but just there. Right? The second L is a little bit more interesting because in 2 weeks we're going to look at another one just very briefly called the LR1. Okay? The second L says this is leftmost derivation, top down. Which token or which rule am I going to take care of first? Which rule am I going to take care of first? Leftmost derivation says if I have a rule AX, I'm going to take care of the A first. Okay? And then expand on the A till I'm done with the A, then I'll go to the X. Okay? The reason the SC is not really leftmost derivation is I can never really take care of the S. Right? Because what's interesting about this rule is the C, but the C comes after. But if it's a rightmost derivation, that is, I take care of what's on the right-hand side first, then that makes sense. I'll take care of all the C's and then just have the S to kind of sort of continue. Right? Then it makes sense. But that's bottom up. Top down is always take care of your leftmost symbol first. Take care of it and then go to the next symbol. Token, rule. Take care of all of that rule first and then go to the next rule, next rule, and next rule. So it simply says it's top down. So the second L just says, yeah, it's top down. Right? And the 1 is one token look ahead. Strictly one token. One token, one rule. No backtracking allowed because we don't know how with a table driven. So what should the grammar have, right? So the prerequisite for the grammar, no left recursion. Unit productions are okay, but it should probably minimize. But you must left factor everything to ensure one token look ahead. You didn't have to do the third one for recursive descent. If you left bunch of rules, it just means try this one. If it didn't work, go back. Try the second one. Didn't work? Okay, keep going back. It's slower, but doable. Here, not doable. You gotta left factor everything. right? And if you already started that process, you know that can be really painful when you have a huge language. When a lot of things that start with a type, int, x, or int, some ID, everything starts with an int or type ID, then that means everything gets sort of lumped to the star symbol, right? So then it's not quite as clean. Okay, so the procedure, first thing we need to do is compute the first and follow sets. And I'm probably not going to get through, um, all the slides today because we have a test. So next week we'll pick up this discussion. Some of this is actually from the reason I have in-class exercise because some of this is actually in the back of last week's slides, but that's okay. We're gonna just start looking at the first. So first set, what is the first token? So if I'm looking for the rule S, what should that token be, the first token? Or if I'm looking for rule A, what token should match? Now, obviously, not all of the tokens will match. Okay, so I'm looking for the first set, which is what are the legal tokens could start this rule. And if I line up the rule, it's actually quite simple. It's really the first column. Right, you line them up. It's the first column. Right, that's your first set. So what's the first set of B? Well, D or E. What's the first set of A? A, little b. What's the first set of big S? Well, little c or O. And big A. What's big A? Little a, little b. Yeah. Okay, so still, everything is in the first column. And notice this one has no lambdas, which makes it a little easier. Lambda just means, okay, something's optional, then I got to skip it over, pretend it's not there, look at the next one. If the next one goes to lambda, then I got to pretend it's not there and look at the next one. Okay, so your first set start to get big just because you could have lambdas. But this one doesn't. I don't even need to look at like anything. Where's my mouse? I don't need to look at anything beyond that first column. None of this matter. It cannot be the first token. First token is that first column. You either match that or you don't. So, okay, imagine this is recursive descent. I'm going to have a function for S. I'm going to have a function for A, function for B. What is B looking for? B is looking for either starts with a token D or E. If it starts with anything else, it's that last else return false. I don't even need to look at it. It cannot be that first. So the first token has to be D or E. Then I have a chance of making it through. If the first token is D, then I can try the big B again, right? And try the big, right? But if the first token is not D or E, then there's nowhere else to go. So that's what first tokens are for, or the first set is used for. And if you don't have lambdas, well, that makes it pretty easy, right? So the algorithm for this, you don't even really need the algorithm, right? So first set, you don't really need the algorithm. You just look at it. Okay, so the colors didn't show through. That's supposed to be red, that first column. So it's whatever that first column is. If it happens to be a big letter, non-terminal, then go to the non-terminal and decide. Mouse keep going back. Okay, go to that non-terminal and decide. Okay, so big A, so it has to be A, B, or C. So the first set for this grammar is DE for B, AB for A, and C, and then AB for big A. Okay? No lambdas, no complications, nothing else to consider. That's it. So what could cause problem? I can almost see this right away since there are no lambdas, right? If I have rules that were 2 A's, 2 B's, 2 D's, 2 E's, or a rule where the big A also, has C in it, okay? Then if I have more rules than first set, okay? So if I have more rules than first set tokens, most likely I'm going to need to left factor because, right, so I have 2 rules for B 2 first set tokens. 2 rules for A, 2 first set tokens. 2 rules for S, 3 first set tokens. Okay, so it's okay because this is a set, so I don't, there's no duplicates. They're all unique tokens, right? So if A somehow had a C in there as well, okay, then I may have issues. Okay, so, but at least at a first look, I got more first set tokens than there are rules. So that means I don't have a same token mapping to multiple rules. So that's a good sign. There's no guarantee that it still works, but it looks like this one should work since it's pretty simple. There's nothing there that prevents it from working. What about lambdas? Okay. What about lambdas? Okay, lambdas. Well, you still highlight your first column. Okay? If there's a lambda in the first set or the first column, put it in. Okay, put it in. So A's first set is A, B, and lambda. Sure, you highlighted the first column, put it in. Okay, lambdas require some extra work on the follow set, but for the first set, yeah, we'll put it in. What about first set of S? Now it has big A in it. We do not put lambdas. Right, even though on the previous slide, what we said was, oh, whatever the A's first set is, put it in for S because S starts with A, right? But now the first set of A has a lambda in it. We do not put a lambda into S because S itself, notice, does not go to lambda. S has to have at least a C in it, right? If S itself could go to lambda, okay, how would it go to lambda in this case? Well, if A were to go to lambda and B were to go to lambda as well, then the S itself could go to nothing, lambda. Then you put the lambda in. Otherwise, you do not copy the lambda, right? Do not copy the lambda. So what's the first step for this with a lambda? Only thing extra is the A has a lambda in it. But is that correct? Hope it's not correct. It's like, I gotta have another slide. Okay. I always say cover it up, and I don't know if that visual helps. And it helps me when I try to figure these things out. Okay, so and we say, okay, that's my first column. Okay, that's the first column. Right? So whatever that thing results in, A and B. Yep, that's my first set. But A could also go to lambda, which means it's not there. A just lambda, it's not there. So I always use eraser to cover it up. Yeah, what if A was not there? Then it's not the first column anymore, right? B is now the first column. So if A would go to lambda, then you just have B left. A is not there. Then you got to consider, how should S start? Well, S could start with a C, could start with A or B, or it could start with D or E. Just go have A goes to lambda. What does that look like? This A goes to lambda, B goes to E. Yeah, S is E. Sure. Okay, so that means anytime you have a lambda, and this could be a whole bunch of these, you have A, B, C, all three of them could go to lambda. Anytime you have a lambda, you got to keep going. Your first column shifts to the second column, and the third column, and the fourth column if necessary. It keeps going until it no longer, right, until it gets to a token, basically. And I got to a token, D or E, no lambdas. Yeah, so it's got to start with D or E, or A or B, or C. So my first set just got big, big, right? But there's still only two rules. Okay, so here, my first set is A, B, C, D, E. 5 first set tokens, 2 rules. My chances are good. They're not going to fight, right? But it also means a rule is going to get used more than once per token, right? So which token goes with which? A, B, C, D, E. Oh, I know this one. The C is easy. Yeah, that rule. Yep, I got a rule that goes to C. I have 4 more tokens, only 1 more rule left, so there's no choice. I'm not changing the rules. I'm not changing the rules. It's just still 2 rules for S, A, B, or C, little c. Little c goes with the C token. Big AB goes with A, goes with B, goes with D, and goes with E. Okay, because the D and E because of the lambda. Okay, D and E just says, yeah, A didn't exist. Okay, you can see the fading. So A didn't exist, so I have B. Okay, and that if A has something, okay, use that, A or B. Okay, so the first column shifts if you have lambdas. Okay, if you didn't have lambdas, just the first column. So it makes the things a little easier. So first set is the easy one. Have any more examples? Oh, good. Okay, more examples. All right. So this one, again, we circle the first column, right? So A's first set is A and lambda, B's first set and B and lambda, and that's it. They just have tokens. S's first set is A, first column, which is A. Don't copy the lambda unless S itself goes to lambda. So you get A here for the big A. But if big A goes to lambda, then you actually have B. Okay, so little b. Again, we don't copy the lambdas in. Right? But if both of them go to lambda, then you have C. So now we shift the first column to the third column. So C, A, B, and C. That's how we computed the first set with lambdas. I'm doing on time. Okay, so I'm going to go back to the very first exercise. I had time. Normally I had you do this, but since we don't have a lot of time today, we will do more exercises before the homework and before I had you do something with this. Okay, so this is very similar to what we just saw. C has P and Q. B has G, H, and lambda. A has E, F, and lambda. S, okay, so instead of just A, B, C, now it has big A, big B, big C, and big D. Again, the colors didn't come through, but big A, lambda, big B, lambda, big C, no. Okay, so it's going to stop at C, okay? It will never start with a D because C has to exist. So big A's first set, EF, no lambda. Big B's first set, GH, no lambda. Big C's first set, PQ, no lambda. That's it. We don't go all the way to the D because C is stopped. So that's the last column we're going to consider, right, as the first set. So, and we do this with not just A, B, C's, and D's, and E's, and F's, but we do that with real grammar, right? So whatever the first token is, and in our mini C, for instance, a lot of things starts with a type. Int, double, okay, whatever the type is. If you have a data decoration, starts with a type. When you have function prototype, starts with a type. When you have function definitions, int main starts with a type. Bunch of things starts with a type. So my first set has type in it. Some statements starts with ID, X equals. Some statements starts with a keyword, if, while, do, for, okay, keywords. Okay, so those are all first sets. If I'm looking for a while loop, obviously the first token I'm looking for is while. If it's not while, then it's not a while loop. Okay, it's something else. Okay, so that's how we use the first set. Even in the recursive descent, which we didn't talk about as being necessary, but yeah, even in recursive descent, we could utilize the first set. Yes.
On that last table,
this one.
Yeah, why did the D disappear? I don't understand that.
The D. Oh, it doesn't get to D because C doesn't have any lambda. So what is it?
So it always has to be.
What's the small? Yeah. It's going to be either PD or QD. That's the smallest word possible. A and B could drop out because the lambda, but I still need a P and D or a Q, D. So, yeah, okay. So this is the easy one. Even with a lambda, you got to shift. This is actually the easy one. The follow set usually takes a little bit of explanation. And I have about 10 minutes, so I'm just going to cover sort of the reasoning that we might need the follow set. And we saw the reason actually last week, in the recursive descent. One of the ways we handle lambdas in recursive descent, just say, if I can't use it, it must be true. True, somebody else can use it, the token, right? The follow set, or the table-driven parsers, this is actually not the case. We don't put lambdas in all the tokens. If you don't, whatever tokens you gave me, you're true. We're only going to put lambda true if the token that's supposed to follow is there. Okay, so here's an example. Erase something. Okay, erase this. Here's an example. Example. Dozen times. What does it match? A, B, B. Same number of A's, same number of B's. Right? So when you construct the parse tree for this, it's top down. It's perfectly okay. It's top down. A, S, B. This allows me to pick up the first A. Right? Top down. Token, rule. Token, rule. Okay, I have another A. So ASB. Second A. Done. I have another A. A, S, B. This S. I have a B. I look at my rules. No B. It does not have B. Is not the first set. Okay, so I'll just take the lambda. And this is where we call true. True. And the rest of the function, as you come back from recursion, picks up the B, picks up the B, picks up the B. There were, in fact, because you call S 3 times. Okay, 1, 2, 3. So when you came back, B, B, B. Okay, that's how the stack is used. It's called push-down automata. In this case, just function calls. We call this true regardless what the token is. It didn't have to be a B. The token I could not use, you're true. With the LL1 parser, however, we're actually going to compute what should come after the lambda. What should come after the lambda is B. A, B. If S drops out, what's left? B. It should not have anything else. If you have A, C, C, I could call it true. And then when I come back here and go, oh, wait, the C doesn't match the B. Yep, no. Right? That's what you call the error. But here I could just say, well, if I don't have a B as my next token, it's not true. Don't even bother with true. It's false. If it's a C instead of B, that because I know that B, little b, follows big S. Right? If S were to drop out, what's left? B. This is the easy one to see, right? Because there's a token right after it. If S drops out, what's left? Well, little b. That's case number one. That's really, really easy. What should follow big S when you're completely done? Nothing. And Unix will use $sign, right? Nothing. If I'm done with this big S, everything is parsed. I shouldn't have anything left. A, B, 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 done. What if I had an extra B? Well, it doesn't belong there. After I'm done with S, I shouldn't have anything left. It doesn't belong. That's an error. Okay, so those are the two very first easy follows. Right? Rule number one, when you're done with the symbol, star symbol, completely parse through everything, you shouldn't have anything left. Nothing follows S when you're done. $sign follows S. End of input. When you have a rule like this where there's a token following a big non-terminal, then that token follows that. I don't even care what this side is. Not looking at that side. I'm looking strictly at the rule itself. A, S, B. B follows big S. Right? I don't care what the left-hand side is. So this is one rule I can compute a follow, and there are two more. So I'll go through the first two, the easy one. The other two are a little harder to see, especially with lambdas. So I don't want to confuse you too much. Okay, so first rule, if S is the star symbol, then add the $sign, which is the end of input, into the follow set of S. Okay. Second rule or case, second case, if you have a non-terminal, if you have a non-terminal followed by a token or terminal, and that terminal follows, you have a big letter and a little letter. The little letter follows the big letter, okay? So the little b follows the big A. I don't care what's on the left-hand side. This over here, doesn't matter what that is. Don't care. What I care is that the little b follow the big A. So the little b goes into the follow set of A. Okay, so I can get the follow set that way. And then actually case 3 is not bad. Case 3 is two big letters, big A, big B. Well, what follows big A? Whatever big B is. Lambdas or no lambdas in the follow set. I don't care if the first of B has lambdas in there. We don't put lambdas in the follow set at all. So lambdas is taken out. Do I have an example? Okay, case 4 is hard. So let's just deal with the first 3 cases then. Okay, here's a quick example. My big A, big B, C is S, C, A, B, B, D, B, and E. Okay, first case, S is the star symbol, so it gives a $sign. Second case, the little C follows the big B. See that, A, B, C? And there's no lambdas, so nothing drops out. So C just follows the big B, and so you get a little C in the follow set of big B. Okay. There is no case 3. There's case 4, which we'll cover next week. And there are no lambdas here. Why is lambda tricky? If B were to go to lambda, then B drops out. And the little C could follow A. Okay, so lambda gets a little trickier. You got to consider all the cases. Some things could drop out. Okay, so those are the only two from case 1 and case 2. There's no case 3. And oh no, there's case 3. I'm sorry, there is case 3. Big A, big B. Sorry, I missed that. There is case 3. Okay, so big A, big B. B follows A. What is B? D and E, right? So D and E follows big A. So that goes into big A's follow set. Okay? So for case 1, 2, and 3, we have not looked at the left-hand side at all. We're strictly on the right-hand side. I'm looking for patterns like a token, a low letter following a big letter. I'm looking for 2 big letters together. Okay? Those are the cases I'm looking at. I haven't looked at this left-hand side at all. Case 4, well, we'll have to look at the left-hand side and the right-hand side together. Okay? And also, I haven't given you a lambda in this case, so but the lambdas it's just more. It's going to be more, right? So you just have to consider like moving, like we move the columns for the first set. For the lambdas, we're going to start dropping off stuff, have stuff like jump over. Okay, so that's it. That's what lambdas. And it turns out, even though lambdas are kind of a pain, it turns out that if your entire grammar does not have a single lambda in it at all, you don't need the follow set at all. This one, we went through the exercise of computing the follow set, but you don't need it. There are no lambdas. Nothing can drop out if you don't have lambdas. So computing the follow set is really useless. I don't care what follows. Everything has to be there, right? Only when things drop out, then you want to look at the follow set. What could be lambda? What's legal after this thing goes to lambda when it drops out? Okay, so this one doesn't. Really, the first set is all you really care about for this one. And again, the first set for this one, there are no lambdas. So DE for B, AB for A, and ABC for S. Right? You don't even move a column. Everything is just that first column. That's it. Okay. So this stuff, I haven't assigned the homework for this one yet because we're not done talking about it. I really do want to go through more example and have you do some exercises in class before I assign the homework. So I think this is probably a good stopping point since it's 7. So let's take a short break and I'll come back for the tests.